Then let me introduce Jürg. Well, first of all, thank you very much that you agreed to give us this this colloquium. Your unique, your style is very recognizable in theoretical and mathematical physics. You have this unique blend of theoretical insight and mathematical rigor that I personally admire. You have received numerous prizes, too many to name them all: the Danny Heinemann Prize, Max Planck Medal, Poincaré Prize, and others. You remember various academies, Berlin-Brandenburg, the US National Academy of Sciences, and so forth. Let me
no, I don't.
And it's a pleasure to have you, and we're curious about what you have to say about quantum mechanics as a complete theory. Thank you.
Thanks a lot for inviting me. I sort of regret that all these talks are now online via Zoom. I prefer the, talks in lecture halls with blackboards and so on, but maybe it's better than nothing. So probably you have heard some of what I'm going to say today, but there are a few somewhat novel elements in this lecture. So here is a table of contents. I will tell you what's missing in textbook quantum mechanics. Then I will say how to unravel the Schrödinger von Neumann equation. I will briefly comment on Huygens principle and how it applies to a completion of quantum mechanics. And then I will look at an example, namely the example of fluorescence of two-level atoms coupled to radiation. So, of course, this is the result of joint work with various people, in particular with my last PhD student, Baptiste Chubnel. All right, so here is, maybe, let's see. So, you see, I would have liked to talk about the relativistic version of this story, where locality and the spectrum condition and so on play an essential role. But it seems to me the whole idea, circle of ideas, is not sufficiently well known yet. And then in 1 hour, I cannot possibly really explain what the local relativistic variant of this whole business looks like. Maybe this is for next year or so. Anyway, so, oops. So let's now first explain what's missing in textbook quantum mechanics. Of course, you all know textbook quantum mechanics, so I can be very short about it. But I would like to recall that it is a theory that makes reliable predictions only about average evolution of ensembles of very many identical systems. Without additions and amendments, it does not make reliable predictions about the evolution of an individual system. And it does not have a clear ontology. This word ontology, of course, is one of the favorite words of people who worry about the foundations of quantum theory. Well, this deficiency was already recognized shortly after the discovery of matrix mechanics, and people including Bohr, Born, and Heisenberg attempted to remedy it by garnishing the theory with an interpretation, the celebrated Copenhagen interpretation, which I will now briefly recall. A physical system in quantum mechanics is characterized by a family O sub S of bounded self-adjoint operators that represent physical quantities characteristic of the system. No, doesn't want to. Oh, no, okay. So, general states of the system are represented by density matrices, and as a special case, pure states are represented by orthogonal projections of rank 1. In the Schrödinger picture, the time evolution of a state, omega, of an isolated system is described by the Schrödinger von Neumann equation, omega dot of t equals minus IH bar, commutator HS of t with omega t. Except, one says, at instances when a measurement or an observation is made. S is autonomous if its Hamiltonian HS of t is independent of t. I will mostly look at autonomous systems for simplicity. This equation 1 is a linear deterministic evolution equation. Of course, this cannot be the full story, and Einstein already recognized that in 1916 in his analysis of spontaneous and induced emission and absorption of light by atoms, where he introduced randomness into quantum theory. So let us suppose that some physical quantity of the system S, represented by an operator X with discrete spectrum, is measured. X can be diagonalized, as in Formula 2. The xi's are the eigenvalues of X, and pi sub xi is the eigenprojection associated with the eigenvalue xi. We want to understand the effect of a measurement of this quantity X on the evolution of the state of the system S. There are 2 points of view. The first one is about the behavior of ensemble averages. So let phi be an ensemble of very many systems all identical to S, and let omega in denote an average over the states of all systems in E just when a measurement of X begins. Then von Neumann formulated a postulate in his famous book. It's usually represented in a slightly wrong way in the books. The average over the states of all systems in E at the end of a measurement of X is given by a density matrix omega out that commutes with all eigenprojections pi sub xi of the operator that has been measured, and with the property that the Born probability of measuring the eigenvalue, the value xi for X in the out state is the same as the probability of measuring xi at the beginning of the measurement. This postulate is compatible with a linear deterministic evolution equation, for example, given by a semi-group of trace-preserving completely positive maps on density matrices, if the experimental equipment used to measure the quantity X is not included in the definition of the system. So the probabilistic aspect of quantum mechanics doesn't really appear in von Neumann's postulate. So, however, experiments show that every measurement of quantity X on an individual system results in a measured value of X given by an eigenvalue xi of this operator. However, results of measurements carried out on individual systems can usually not be predicted with certainty, but only frequencies of measured values can be predicted. And this is captured by Lüder's measurement postulate, which is also usually stated in a somewhat wrong way in the books. If an individual system identical to S is prepared in a pure state, given by a unit vector psi in, at the moment when a measurement of X begins, then its state at the end of the measurement corresponds to a unit vector psi out belonging to the range or image of one of the eigenprojections pi sub xi for some eigenvalue xi of the operator X, and it will be this xi that will be measured. The probability that psi out belongs to the range of pi xi is given by Born's rule, by the usual Born rule. All right, so that's Lüder's postulate. Oops. Now, in Lüder's postulate, an element of chance finally enters the quantum formalism. Apparently, the evolution of the state of an individual system during the measurement of a physical quantity, according to Lüder's, is certainly nonlinear and stochastic, and it exhibits quantum jumps. Now, there are some weak points in this interpretation. Point 1. To put it short, what does one mean by a measurement in quantum mechanics? What is different in a period when measurements happen from periods when without measurements? Lüder's postulate appears to presuppose that there are observers who decide which measurements will be carried out and when they will be carried out. This, of course, takes out essentially all predictive power from standard quantum mechanics. Point 3, the assumptions implicit in the Copenhagen interpretation that one can choose the exact moment when a measurement begins, and 2, that there are measurements that take arbitrarily little time to be carried out, which would result in infinitely strong fluctuations of energy, strike me as completely absurd. Point 4, radioactive decays or the fluorescence of an atom are stochastic processes involving quantum jumps, but there's no observer present to trigger them. So we have to ask what's going on. Where does probability in quantum theory really come from? Let me mention some fake cures of textbook quantum mechanics. One, I regard de Broglie-Bohm theory as not an entirely acceptable cure of the problems of textbook quantum mechanics. It reminds me of the ether hypothesis because it introduces objects, namely the Bohmian particles, that appear to be fundamentally unobservable. I also don't like the GRW wave function, spontaneous wave function collapse mechanisms very much. They remind me of electromagnetic or mechanistic explanations of Lorentz contraction, all of which were eliminated once the special theory of relativity was found. And of course, I don't like too much Everett's many worlds interpretation or relational quantum mechanics, etc., because these are schemes that look to me very vague. They sort of remind me of the Pauli-Jung theory of synchronicity. One never really quite understands what one talks about. So we have to try to do better. Now, I would like to digress on an analogy of quantum theory with Brownian motion. And this is in order to guide our thoughts in the right direction. Imagine that E is a drop of a substance, for example, ink, eosine, suspended in a liquid, for example, water, that is in thermal equilibrium at some positive temperature. The state of this drop at time t is described by its density, rho sub t, which is a non-negative function of physical space, normalized such that its integral is equal to 1. The time dependence of rho sub t is governed by the diffusion equation. Rho dot of t equals d Laplacian applied to rho of t. D is the diffusion constant. And this is obviously a linear deterministic law of evolution. The solution is well known in terms of the He kernels. And now, of course, according to the atomistic view of matter, E really consists of many identical point-like particles, for example, the eosine molecules, that are assumed to be sufficiently far apart here from one another that one can neglect interactions. The density rho sub t can then be interpreted as an average of the states of these particles, which are given by their positions on physical space. All right, an individual system that we talk about here consists of a single particle in the ensemble E suspended in the fluid. According to Einstein and Smoluchowski, its Brownian motion arises from random collisions with clusters of the fluid molecules, and from this they derive, for example, a famous expression for the diffusion constant. The ontology then is the following. Point 1, at every time t, a particle in the ensemble E is localized in a specific point x sub psi of t in physical space, and the trajectory of a particle, I denote it by psi, is a random continuous curve, a Brownian path in physical space, as indicated in this nice figure that, of course, I took from Wikipedia. All right, so that's the ontology. Now, as shown by Norbert Wiener, there is a probability measure dW of Xi and the space capital Xi of particle trajectories starting at some point x naught in physical space at time t naught. This measure is supported on trajectories Xi that are Hölder continuous of index 1/2, and in particular the velocity of a particle in this ensemble E is never well defined according to Wiener. An event at time t in this system is the manifestation of the position x sub Xi of t of the particle. Therefore, Xi, its trajectory, can be viewed as a history of events. It's a random object, and the space capital Xi can be viewed as the space of histories. The Wiener measure allows us to predict probabilities of measurable sets of histories of such particles. One example is to compute the probability that the trajectory of a particle reaches certain subsets O sub I in physical space at various times Ti. And that can be computed as a Wiener integral over a product of certain characteristic functions. This particular formula, people have this hang-up that they would like to extend this particular formula to quantum mechanics, but turns out that doesn't really work. Using Wiener measure to take an average over the ensemble E of very many identical ink particles, one recovers the deterministic law given by the diffusion equation, as I write here in this equation 7. All right, so that's what happens with Brownian motion. Now in quantum mechanics, we would like to do the same thing. We would like to pass from an ensemble description of quantum systems to a probabilistic description of the evolution of individual systems. That's really the goal. So we now want to unravel the Schrödinger von Neumann equation. I propose a completion of quantum mechanics that is based on such an unraveling. The upshot of my analysis will be that the Schrödinger von Neumann equation can be understood to arise from taking an average over the random histories of many identically prepared systems. The ontology of quantum mechanics lies in random histories of events, and quantum mechanics equips the non-commutative space of such histories with a quantum probability measure in analogy with the Wiener measure for Brownian motion. Our task is then to find this probability measure. This involves finding an appropriate notion of states of physical systems and describing their stochastic time evolution. The ETH approach to quantum mechanics accomplishes this task. It will be sketched from non-relativistic quantum mechanics, but as I said at the beginning, there exists a local relativistic version of it, which I won't have time to go into today. We will assume that S is an isolated autonomous system, and we will work in the Heisenberg picture. So we will associate with every physical operator representing a physical quantity a concrete operator x of t at every time t. And the x of t satisfies the Heisenberg equations of motion. So it is convenient to introduce some natural algebras. E greater or equal to d, t is the algebra generated by all the operators x of t prime. X belongs to OS and t prime is greater or equal to t. And it is often convenient to deal with von Neumann algebra, so you want to close this weakly. This definition immediately implies that E greater or equal to t contains or is equal to E greater or equal to t prime whenever time t prime is greater than time t. Now we have to introduce the notion of events, sort of following the lead by Rudolf Haag. He was very fond of this notion of events, and I will now try to introduce some such notion. So suppose S is an isolated physical system, a potential future event in S that may materialize at times greater or equal to t is described by a partition of unity by disjoint orthogonal projections. I denote it by frac P. So the pi sub xi are these projections, they're orthogonal and they are disjoint and they sum up to the identity. The following, the symbol little pi will always stand for an orthogonal projection. All right, now an isolated system is characterized by a co-filtration of these algebras E greater or equal to T, and they can now be viewed as algebras of potential future events. If S is autonomous, that means that the Hamiltonian is independent of time, then all these algebras E greater or equal to T are unitarily conjugated to one another simply by the propagator of the system. So they're all isomorphic. In a relativistic theory, they are typically type 3 for Neumann algebras. In non-relativistic systems, they are more typically type 1. So here is a principle. This principle is, something a little analogous to the principle that the velocity of light is independent of the inertial frame in which you measure it. So I call it the principle of diminishing potentialities. It is the statement that the algebra E greater or equal to T contains strictly, properly, the algebra E greater or equal to T prime whenever time T prime is greater than time T. This principle characterizes isolated open systems, namely systems that can release events to the outside world. It can be proven to hold in axiomatic theories of the electromagnetic field. This was shown by Detlef Buchholz many years ago, maybe not quite in the same formulation, but his result is what proves this principle of diminishing potentialities in quantum electrodynamics. It also holds in simple models that we will discuss below. A state, rho sub t at time t, is a quantum probability measure on the lattice of all potential events in E greater or equal to T, which by results of Gleason and Maeda amounts to a normal state on E greater or equal to T. I now do as if this were always a density matrix, and in the non-relativistic case, that's okay. So given a state omega sub t at time t, the centralizer of this state is the subalgebra of this algebra E greater or equal to T of all potential events at time greater or equal to T. That is generated by all potential events for which the state omega t commutes with the projections pi sub xi that belong to this potential event. All right, so that's simply the centralizer of the state omega t inside the algebra E greater or equal to T. P sub omega t is the finest potential event commuting with all the operators in the centralizer. So in other words, P sub omega t consists of the projections that generate the center of the centralizer. Here is a definition. P sub omega t is the potential event. I say that P sub omega t is the potential event that actualizes, that becomes actual at time t, given that the state of the system at time t is omega t. So these are reasonable notions of potential events and potential events actualizing at some time. We are now prepared to introduce a law governing the stochastic time evolution of the state of an individual isolated system. In order to be precise mathematically, I temporarily suppose that time is discrete. In other words, t belongs to z sub tau, where tau is positive, it is an elementary time step. Thanks to the principle of diminishing potentialities, number 10, and the phenomenon of entanglement, the following state reduction postulate is meaningful and that it has non-trivial consequences. Suppose that omega t is the state of the system S at time t. I define omega bar of t plus tau to be the state on the algebra E greater or equal to t plus tau, obtained by restricting omega t to the algebra E greater or equal to t plus tau. Since this algebra E greater or equal to t plus tau is properly contained in E greater or equal to t, one may then imagine that omega bars of t plus tau tends to be always a mixed state. So here is an axiom. Let pi xi in x sub omega bar t plus tau be the potential event actualizing at time t plus tau, given the state omega bar t plus tau. So a potential event actualizing at some time is what I defined in definition 2. It's the center of the center. It generates the center of the centralizer. Oops. Too far. So then nature replaces the state omega bars of t plus tau on the algebra E greater or equal to t plus tau by a state omega t plus tau that is a sandwich of omega bar t plus tau between projections pi sub xi that belong to p sub omega bar t plus tau. And of course, only projections qualify in equation 12 that have a non-vanishing Born rule probability. So the probability of choosing a certain projection pi sub xi is just given by the Born rule. From now on, I call the projection pi of t plus tau equal pi sub xi that appears in equation 12, the actual event or the actuality at time t plus tau. So a history of an individual quantum system consists then of actual events starting at the initial time when the system was prepared and up to the time t of the present. We can associate with such a history operator, capital H, so pi naught. Pi naught is the initial, projects on the initial state of the system, and then a product of the pi of t prime between t naught and t, and belonging to z sub tau. That's a history operator. It's of course an order product. And then the probability of a history given an initial state corresponding to the projection pi naught is simply given by the trace of h star times h. So the axiom CP says that the time evolution of the state of an individual system S is apparently described by a stochastic branching process. I call it the quantum Poisson process. And the probabilities, the branching probabilities are completely described by the generalized Born rule that appears in the axiom CP. All right. So this theory is mathematically completely meaningful as long as the time step is positive. I cannot pretend that I understand how to let the time step tend to zero in general. I can understand it in certain examples, in particular in the examples I will now discuss in the following two sections. The usual Schrödinger von Neumann equation arises when one takes an average over all possible histories of a system. You see here a little drawing, which is a sort of metaphorical representation of this wonderful stochastic branching process that an individual system goes through. The green branches form a tree-like structure. They indicate all the possibilities for how to branch. The blue path is a specific history, and the red dots are the events that happen at different times. All right, so that's a brief sketch of this ETH approach that you may already have heard. It has not become very popular yet, although I think it's maybe one of the few approaches to quantum theory that has some chance of making sense. All right, now I would like to, in honor of Detlef Buchholz, who may listen to this talk, I would like to briefly recall Huygens' principle and tell you how it implies this principle of diminishing potentialities. So the fact is that the Huygens principle for massless modes, photons, gravitons, and so on an even dimensional Minkowski space implies the principle of diminishing potentialities. Let's look at an example. So let's suppose that S is an isolated system that consists of a static atom located near the origin of physical space, which is coupled to the electromagnetic field. In order to regularize the theory of this system in the ultraviolet, I discretize time. So the time step tau or dt is strictly positive. Let's suppose that the atom has m internal energy levels, then its Hilbert space is simply a Cm. The Hilbert space of the electromagnetic field is the Fock space of photons. The electromagnetic field is described by the field tensor F mu nu. And if you smear out the field tensor with real value test functions on space-time, then you get the self-adjoint operator on F that satisfies, that has local commutators, and in fact, the commutator distribution satisfies Huygens' principle in the sense that it is supported on the surface of a light cone. The relativistic spectrum condition holds for this system. In other words, the total Hamiltonian of the system is greater or equal to 0. You might feel a little bit perplexed that I do as if this was a decent system. Of course, a static atom is not a decent system of relativistic quantum theory, but it can be treated as long as the time step is kept to be positive. All right. And now you see here is an illustration of why the principle of diminishing potentialities holds. The time step tau is the difference between these times ti plus 1 minus ti. And in every interval on the time axis from ti to ti plus 1, you can plant the space-time diamond. And then if you look at all the operators, say in the green light cone, they commute with all the operators in the red line cone, you get just the fields that are supported in this little space-time diamond. And so that, of course, that's a big algebra, and so it proves the principle of diminishing potentialities. You can open up these light cones by letting the velocity of light tend to infinity, and then you get time slices. And in fact, the treatment of these models simplifies drastically in the limit where the speed of light tends to infinity. So in fact, that's what I'm going to do in order to be able to sort of present very explicit, solid results to you. I think that these systems could be treated without letting the velocity of light tend to infinity, but it's much harder because of memory effects. I mean, I could digress on that, but let's not. All right. So, I've prepared some slides to explain the details of how Huygens' principle is used to establish the principle of diminishing potentialities. But I think the drawing has more or less explained the basic idea, and so I skipped the following 2 slides so as not to run over time. Now I come to the last section of this lecture, And that is an application of this ETH approach to quantum mechanics to a two-level atom that illustrates the phenomenon of fluorescence. So the two-level atom is coupled to the radiation field. And in order to be able to sort of present results that are relatively simple and mathematically entirely rigorous, I now consider the limit where the velocity of light tends to infinity. The space-time diamonds that you saw in the drawing then open up to time slices, k tau smaller equal to t smaller equal to k plus 1 tau. And functionals of the radiation field localized in different time slices simply commute. The Hamiltonian of the electromagnetic field in the limit where the velocity of light tends to infinity is then simply given by the generator P of translations in the direction of the time axis. Of course, this Hamiltonian violates the relativistic spectrum condition. It's unbounded below. The field algebras of the space-time diamonds then collapse to simply full matrix algebras. They can be infinite dimensional. They could even be finite dimensional if you want to have a very simple model. All right. But then, of course, you know, the principle of diminishing potentialities remains true. The ensemble time evolution of S, of the system of consisting of the atom coupled to this radiation field in the limit where C tends to infinity, this evolution becomes Markovian, provided the initial state of the radiation field is chosen suitably. And so I will try, namely, it has to be chosen in such a way that different time slices are not entangled with one another. So let's do a very explicit example. I look at the model of a two-level atom. And I imagine that every capital T seconds, such an atom is released from an atom source. It's prepared in a superposition of its two internal states, namely a ground state that I denote by spin down and the excited state that I denote by spin up. In less than capital T seconds, the atom propagates from the atom source to an atom detector, where some observable capital X acting on the Hilbert space of internal atomic states is measured. And the measurement can be described completely by using the ETH approach, as you know, as you can read in my published papers with various people. So during the trip from source to detector, the atom might jump from an excited state to a ground state and emit the photon. That's the phenomenon of spontaneous emission that Einstein discussed in 1916. We would like to now apply the ETH approach to quantum mechanics to describe this spontaneous emission process as a stochastic process. It really is a stochastic process. The times of emission are random variables, and we would like to, for example, understand the distribution of these random variables. All right. I will treat different atoms released by the atom source as statistically independent. So there are two different experimental setups, and you will see that they lead to fairly different conclusions. It could be that the photons that are possibly emitted by an atom on its trip from source to detector escape the experimental setup and will never be detected. Or at least they will not be detected before their entanglement with the state of the atom is wiped out by further interactions. The second setup is very different. The photons emitted by an atom are immediately detected by a photomultiplier that clicks before the atom ends its trip to its own detector. So we will discuss both setup 1 and setup 2 and exhibit the differences in the conclusions. So the Hilbert space of the total system consists of the atomic states, the excited and the ground state. The orbital motion of the atom is unimportant, does not appear in the discussion. Then you take the tensor product with the Fock space of the radiation field and the tensor product with the states of the photomultiplier. In setup 1, the photomultiplier is turned off, it will never click, and so you can forget it in setup 1. I will now describe the states of the atom. Let sigma vector be the vector of Pauli matrices. An atomic state is given by a density matrix rho of n. N is a vector in free space. Rho of n acts on C2, on the Hilbert space of internal states of the atom, and is given by 1/2 the identity matrix plus n dot sigma. N is a vector in free space of length smaller or equal to 1. This state is pure. In other words, it's a rank 1 projection if n is a unit vector. Obviously, rho of n plus rho of minus n is the identity, and trace of the vector of Pauli matrices multiplying rho of n is given by the vector n. The matrix rho of n has eigenvalues 1 plus length of n divided by 2 and 1 minus length of n divided by 2, with eigenspaces given by the ranges of the projections rho plus or minus n divided by its length. All right, so that's how I describe the states of the atom. The atomic Hamiltonian is simply given by 1/2 vector of angular velocities dotted into sigma. This vector omega is, for example, oriented in the 3 direction, and capital omega is the angular velocity. If you now conjugate an initial state rho of n naught with the propagator of the system, you get a state rho of nt, and nt is obtained from n naught by simply letting n naught precess around the 3 axis with angular velocity omega. All right. The radiation field is treated in the non-relativistic limit where the velocity of light tends to infinity. States of the radiation field are constructed as follows. I introduce a vacuum for the radiation field. It's a tensor product of states 0 sub k. K labels the time slices, and 0 sub k is a specific, let's call it the no photon state in the Hilbert space of the kth time slice. The Fock space of this caricature of the electromagnetic field is the completion in the natural norm of the span of vectors capital phi, which are given as tensor products of vectors little phi sub k. The tensor products range over the time slices, and phi sub k is equal to the no photon state 0 sub k, except for possibly finitely many values of k. So then you take all linear combinations of these vectors capital phi and close it in the natural norm. By gamma, I will denote the state that contains at least 1 photon. That means that one of these phi of k's should be different from the no photon state for some times slice k. And of course, these states are then all orthogonal to the vacuum. General states of the radiation field are given by density matrices on this Fock space F. The field Hamiltonian is given by the operator P of translations of photon configurations in the time direction. this time evolution will not enter explicitly in the following sketch of results because I will not present the details of the calculations. But I repeat, the Hamiltonian of the field, of course, when you let the time step tend to 0, you obtain an operator that has spectrum that will cover the entire real axis. So the relativistic spectrum condition, of course, is violated because we have taken the limit where the velocity of light tends to infinity. What about states of the photomultiplier? Well, they will not appear in this discussion explicitly. It is important to look at models of a photomultiplier which have the feature that the photomultiplier relaxes back to the dormant, to its ground state, describing the dormant photomultiplier within a relatively short relaxation time. Such models exist. They have been described in, for example, work I have done also many years ago, and also in work of Jürg and Kupjainen and so on. So that's all that matters. The photomultiplier should be dormant as soon as an atom has passed and before the next atom comes along. All right. So we assume that the interaction between the atom and the radiation field is fairly weak, corresponding to a coupling constant whose square is denoted by alpha. That's the fine structure constant, and it is, of course, much smaller than 1. I will now describe the effective time evolution of an atom coupled to the radiation field in the 2 setups. So I start with setup 1, the photomultiplier is turned off. I choose an initial state of the radiation field, not entangling modes at different times. For example, the vacuum state that I described before. The effective time evolution of the atom is then Markovian, and in the sense of, Limplatt and people like that, and it can be determined explicitly. I use the notations that are inspired by the notations I introduced in section 2 of this lecture. I now denote the time step tau by dt. It looks a little nicer then. And the states omega bar sub t plus tau that are obtained by restricting the state omega sub t to the algebra E greater or equal to t plus tau. These states of an atom are now completely characterized by vectors n bar of t plus dt that belong to the 3 space. So we can describe the effective evolution of the atom by deriving an evolution equation for the vectors n bar of t plus dt. And it's given as follows. M bar of t plus dt is equal to the vector n of t that describes the state of the atom at time t. It's a unit vector because at each time the atom is in a certain eternal state. But then it is corrected by an increment dnt. And dnt has 2 contributions. One contribution comes from the precession of the vector n of t around the 3-axis with this angular velocity omega. But then there is a second dissipative contribution that is obtained by applying a certain linear map dk to the vector n of t. So this map is proportional to dt, and it has the property that it shrinks the length of the vector n of t to, when you pass from n of t to the vector n bar of t plus dt, the length shrinks by an amount order alpha times dt. And this happens except if n of t is exactly equal to minus the unit vector in the 3 direction. Then in fact, nothing happens. In fact, n of t becomes constant because then the atom is in the ground state and no emissions are possible. And since the field, since the state of the radiation field is the vacuum, it also cannot absorb any photons. However, as long as the atom is in a state which is not the ground state, but the superposition of the excited state, the ground state, then in fact, the effective time evolution apparently tends to convert pure states into mixtures. Now, of course, we have to apply the state reduction postulate that I discussed in section 2, and that goes as follows. So applying axiom CP, the state reduction postulate, the evolution of the state of an atom is found to be given by a Poisson jump process on the Bloch sphere, namely on the sphere of unit vectors in free space. And it is described as follows: n of t goes to a vector n of t plus dt, describing the state of the atom at time t plus dt, which is given by renormalizing the vector n bar of t plus dt to be a unit vector. And this happens with probability 1 minus order alpha. In other words, with a probability fairly close to 1. And with a small probability of order alpha, n of t is mapped to a vector n of t plus dt, which is the vector n bar t plus dt normalized to have length 1, and then you pass to the antipode. That's this red minus sign that you see in the formula. The rate of this jump process is proportional to alpha. That means that there is roughly one random jump from n of t to the antipode of n bar of t plus dt every order alpha inverse times t seconds. So it's a relatively rare process, but you should just remember that the state of an individual atom apparently evolves in a random fashion. It usually just evolves according to what you would think should happen according to a Schrödinger equation, but every once in a while it jumps to the antipode. And of course, you can sort of imagine that this jump to the antipode has something to do with the emission of a photon, but the photon is not detected in this setup 1. So when entering the atom detector, the state of the atom in setup 1 is given by a density, by a pure state rho n out, where n out is a unit vector which in polar angles is given by, sine theta prime, cosine phi out, etc., etc. Theta prime is close to theta naught with an error of order alpha when there is no jump, but it is close to theta naught minus pi, or pi minus theta naught if there is an odd number of jumps. Okay. All right. So in other words, the out vector n out is obtained from the initial vector n naught by letting it precess around the 3-axis, and then either it is given by the image of this precession or by the antipode of the image of this precession, up to small errors of order alpha. That's what happens in setup 1. Now we go to setup 2. If the photomultiplier is turned on, then according to the ETH approach, the time evolution of the initial state of atom plus radiation field, the radiation field being in the vacuum state, to the final state when the atom enters the atom detector is given by either psi in goes to psi out, which is given by a rho n out, it's a pure state of the atom, times the vacuum of the radiation field, where n out is basically simply obtained by letting the initial vector n naught precess with angular velocity omega, or And this happens with large probability because the probability of spontaneous emission is small, it's order alpha. And with small probability order of alpha, one or several photons will be emitted, and then the out state is the atom in the ground state times a state of the radiation field that contains at least one photon. All right, that's what happens in setup 2. And you can see that the out state of the atom in setup 1 and in setup 2, these out states are quite different from one another. So apparently, trying to detect the photon that might be emitted affects the evolution of the atom. That's, of course, not too surprising, but it is a little surprising that you can discuss it very explicitly. And in fact, you know, when you look at these, the details of these calculations, one has a complete control of the stochastic, of the Markov chain, so to say, the quantum Markov chain that describes these random processes. So apparently the ETH approach provides a mathematically precise treatment of this model of fluorescence, at least in the limit where the velocity of light tends to infinity. And in fact, for this model, in the limit where the velocity of light tends to infinity, you can pass to the limit where the time step tends to 0. This is, of course, not possible as long as the velocity of light is finite, because you need to have a positive time step to regularize the model in the ultraviolet. So I tend to believe that this theory of fluorescence is really a slightly new development. When you look at the literature, you will find, for example, papers by Yves Beaumont and Lebert and one with Jean Ginibre, where they sort of invent an ad hoc stochastic process to describe fluorescence, but it's in no way derived from basic principles of quantum theory. And these papers by Beaumont and collaborators are fairly recent, and they made a big story out of it, but they were unable to derive the details of their theory of fluorescence from fundamental principles of quantum theory. And here, this has now been possible, as I hope I have sketched. So let's summarize and conclude. The ETH approach to quantum mechanics, the general features of which were described in this section 2 of this lecture, provides a completion of quantum mechanics that leads to a logically coherent description of the stochastic time evolution of states of individual systems in quantum mechanics. This unravels the Schrödinger evolution. It describes random events and their recordings. It has some resemblances with many worlds, but it, in that it describes branching indexed by events. It has some resemblances with GRW, Girardi-Rimini-Weber, because it employs a state reduction postulate, but it supersedes these fairly imprecise formalisms, and it describes only one world, hopefully ours. Of course, it will have to stand the test of experiments. It makes fairly specific predictions, as I hope I have shown in this section 4. And, it could happen that the experiments tell us something different. Then we have to go back to the drawing board. As in the foundation of relativity theory, fields describing massless modes and the even dimensionality of space-time and locality appear to play key roles in the foundation of the principle of diminishing potentialities, which is definitely a cornerstone of the completion of quantum mechanics that I have sketched here. If I had more time, I would have told you a little more about how to describe measurements. I can assure you that there is no measurement problem in this particular completion of quantum mechanics. The ETH approach to quantum mechanics introduces a fundamental arrow of time, namely a distinction between past and future, a distinction between actualities or facts and potentialities, quite in the sense in which Aristotle originally introduced these concepts. And I just finished this talk exactly at 6 o'clock. I thank you for your attention. Of course, I take questions.
Thank you for this interesting talk. Are there any questions? Either raise your hand or speak up.
Apparently there are no questions. That's always a little depressing. If there is absolutely no question, it means that either it was trivial or it was ununderstandable.
I have one. Maybe I start. So this frequency of events, this tau, is that something that's set by is that a scale set by the theory or the state, or is that a universal?
No, sorry.
Thing, or is that supposed to be taken to zero?
Oh, you mean the time step?
Yeah.
Oh, that's just a regularization. You see, if you want to do, for example, a relativistic model where the velocity of light is finite, and you look at the static atom coupled to the radiation field, that's of course not described by a local relativistic quantum field theory. And if you want to describe it by quantum electrodynamics, you run into ultraviolet problems. However, the moment when you make time steps positive, the model makes perfect sense. And it can be shown, and this is not difficult, it can be shown to satisfy this principle of diminishing potentialities. So that's why, you know, if you permit yourself to discretize time, then you have a big reservoir of rather interesting models.
Yeah, so my question is really, how often do the events occur, really independent of technicalities?
So,
would you say, in the real world?
Oh, okay. So in the non-relativistic setting, they keep occurring. There's a continuum flow of events. However, you see, I should have maybe mentioned that. Let's go back to the state reduction postulate briefly. So you see the projection pi that appears, or pi sub psi that appears in the state reduction postulate has the property that its Born probability is usually very close to 1, while all the other pi psi primes that appear in the same potential event that actualizes have very tiny Born probabilities. Now, if you choose if nature chooses the projection with a Born probability very close to 1, then it looks as if the evolution of the state were trivial, as it should be in the Heisenberg picture if you look at textbook quantum mechanics. However, every once in a while, you make a jump to a projection pi of psi that has very tiny Born probability. Why is that? Simply for entropic reasons. You see, think of a spin chain in a magnetic field, then usually the spins are all aligned with the magnetic field, but every once in a while there is a little spin that looks opposite to the magnetic field for purely entropic reasons. So in other words, the evolution of a system, at least in the limit where the velocity of light tends to infinity, the evolution of the state of a system in the Heisenberg picture tends to be almost trivial, except at certain rare times when you experience a quantum jump. This has been discussed in a fairly quantitative fashion in a paper which I wrote with Alessandro Pizzo. It's probably a paper that has never been read by anybody except for the authors, because people believe that one cannot improve quantum mechanics over what one finds in the textbooks. I happen to have another opinion. In any event, in that paper, it is sort of described rather neatly how the evolution, the properties of the evolution, taking into account the events that happen. In any event, the evolution, the Schrödinger evolution, is never exact. It is always corrected for an individual system by either very tiny, almost unnoticeable quantum jumps, and sometimes by a very drastic quantum jump. Of course, if you then take many identical systems and you take an ensemble average over all these systems, then you get the usual evolution given by the Schrödinger von Neumann equation. Does that more or less, was that satisfactory? I believe
I'll take my pick from your answer. We can discuss maybe more another time, but thanks for the answer. Henning.
I should maybe add one comment. I believe in the relativistic world, the events have a sort of discrete nature. They will not happen continuously. But, that's a long story and I cannot go into it. But I think it's a story that should interest people who know more about operator algebras than I know. I think it's an interesting story. Anyway.
That's very interesting. Yeah.
Let's pass to Henning. Henning raised his hand a long time ago.
Thank you, Jürg. My question is closely related to Stefan's. I'm not sure whether you actually have already answered it, but
we'll see.
So you mentioned this problem that you don't know how to control the limit when this time parameter tau goes to 0.
In general, yes.
Yeah, in general. So my question is, in a two-state system, like a spin system, when your Hamiltonian is bounded from above and from below, should that not be very helpful to study this limit?
Yes, that's what I mentioned. Maybe you were not paying attention. You see, in the last section, this fluorescence business, if you look at the limit where c tends to infinity, you can let the time step tend to 0. So that
okay, I must have missed that point. And here you said something that by this limit of letting c going to infinity, you have the photon Hamiltonian, which, you always have the photon, which is unbounded. But
yeah, that's right. You see, let's look at the picture. What does the Hamiltonian of the photons do when you apply it? Apply e to the I tau h field to field operator, conjugate field operators by e to the I tau times h field. And it moves the field from one diamond to the next one. So it just translates along the time axis. If you now let the speed of light or the velocity of light tend to infinity, these diamonds open up to time slice, and the photon, what is the natural limiting photon Hamiltonian, simply moves from one time slice to the next one. But the algebras of the time slices, they are, as long as C is finite, they are type 3 algebras, but in the limit, when C tends to infinity, it becomes just type 1, full matrix algebras. And then, in fact, the Hamiltonian is simply the translation operator in the t direction, which has a spectrum that fills the entire real axis. It's a little like...
Okay, thank you. So maybe Roberto has another question.
Yep.
Thank you very much.
I'm curious about experiments. Do you think there will be experiment in the near future to check your theory, or what's the situation about that?
So I hope I understood it. The transmission was a little bit garbled. But you see, these quantum optics experiments that I was catching, these fluorescence experiments, I think could really be done. I don't know how difficult it is, but I think this could be done. And then you could see whether the predictions I make in these two different setups are verified by the experimental results or not. So I think it's a possibility to test the theory. But I'm sure there are other possible tests of the predictions.
Thank you.
Very good. So maybe this exhausts the questions. Is that right?
It seems there are no further questions, but if there are, please speak up or raise your hand. I don't see a raised hand.
You know, if anybody discovers the question later on, of course, you can contact me by email, and you can also have copies of these slides and so on and so forth. All right, well then, thanks a lot for listening, and I wish you all a very wonderful evening.
Good evening to everybody.
Bye-bye.
Bye-bye.
Bye.
Bye.